We are here to present our project titled IoT based home automation developed by our team Arya, Tarun, Chakradhar, Manikanta. In this project, we have explored how IoT technology can be used to automate everyday home functions like lighting, temperature control, and water management. For our simulation, we made a few assumptions. All the peripherals are stimulated, no real time hardware is interfered here. Our project is dependent on following apps and softwares: Blink IoT app, Arduino, PixinLab, and virtual serial ports for operation. There are no major constraints identified during simulation. The project has three main components: garden lights control, temperature control system, water tank inlet and outlet valve control. Together, these modules help us to automate and remotely manage common home utilities. In the garden light control system, we use LDR sensor to detect intensity of sunlight. Based on the light level, we automatically vary the brightness of LED to stimulate how garden lights can be controlled according to sunlight availability. For example, during daytime, the light remains off, while in the evening, it gradually brightens. Garden control process. The process is simple. The input is taken from LDR sensor. The sensor reads the value and map it to LED brightness, and the output will be seen in garden light brightness automatically adjusted. This demonstrates energy efficiency and intelligent lighting control. Next comes with temperature control system. The temperature control system uses a LM35 temperature sensor, a heater resistant and cooler. It reads real-time temperature data, displays it on both CLCD and Blink app, and allows remote control through IoT app. User can switch on or off the heater cooler from their respective phones. The input is taken from LM35 temperature sensor, which is processed by Arduino and reads its values and gives temperature data. The output will be displayed as Blink widget gauge and also in CLCD screen. This ensures easy monitoring and precise temperature management. Next comes with cooler control system. In this system, we have two control modules. For the cooler, when button on and blink cap is set high, then the cooler turns on, otherwise it remains off. For the heater, similarly, a high logic signal turns on the heater and the low turns it off. This allows user to remotely manage home environment. We have also implemented an automatic threshold system. When the temperature exceeds 35 degrees centigrade, the temperature turns off automatically and the message temperature high, heater off is displayed on CLCD. This improves safety and saves energy for our future generation. The third major part of our project is water tank automation. Here water level is monitored through serial communication. The Arduino displays the water volume on both the CLCD and Blink app. User can control the inlet outlet valves directly from their mobile devices. The system reads the water volume through a serial tank sensor and sends it to the Arduino. The Arduino then displays this data on a gauge widget in the app and on the CLCD display. This gives user a clear and real-time view of tank status. The control of the inlet valve. The inlet valve can be operated through button on Blink app. When the button is high, the inlet valve opens to fill the tank. When the logic is low, it closes automatically. This helps in preventing overflow and reduces manual effort. Out valve control. The out valve works in a similar way. When the temperature, when the user presses the outlet button on the Blink app, the Arduino detects the signal and turns on the outlet valve to release water. Once the required level is reached, it can be turned off with a single tap. Automatic volume control in water tank. The system also has an automatic control logic where if the tank volume drops by 2000 liters, the Arduino automatically turns on the inlet valve. At same time, it sends a notification Blink app, mobile app, and displays the status on the CLCD screen. This ensures efficient water management without manual supervision.
Okay, myself Mankanta. Now I'm going to explain about Blink IoT. Now here you can see these three lines, first three lines. These three lines connect our Arduino project to the Blink IoT cloud. The template ID and template name identify our specific project on Blink. The authenticate token is like a password. It links the Arduino board with the Blink app on your phone. So when we run this code, Blink knows which project and device to communicate with. Now we can see these libraries. These libraries help our Arduino connect to the internet using an Ethernet module and communicate with the Blink IoT cloud. Now we can see these functions. Blink write. Blink rate is a function called every time device gets an update of virtual pin value from server. And we can see param dot as in to interpret incoming data as integers, floats, and strings, etc. We can also use blink virtual write function which send data in various formats to virtual pins. And also we have blink timer dot set interval which calls function after every particular period of time. So we have so many functions, and in the blink part of code connects our Arduino to the IoT cloud, lets us control devices like the cooler, heater, and valves remotely, and displays live readings such as temperature and water volume on the mobile app. It makes the entire home automation system smart, wireless, and user friendly. Now we can go to the main part, which is garden lights control. Here we use two main components, which is LDR light dependent resistor and LED light emitting diode. Here LDR plays a major role. Basically, LDR is a resistor that changes its resistance according to intensity of light. When the LDR is in dark, it has high resistance and produces the logic high value at the output. And when LDR is in light, the resistance value of LDR decreases and the output it gives the logic low voltage. We have mainly two components, which is resistance and voltage mainly takes place, which is sunlight is directly proportional to voltage and inversely proportional to resistance. When we have when we are in dark place, when sunlight is low, then resistance will be high and voltage will be low. When sunlight is high, voltage will be high and resistance will be low. The key objective is to reduce manual operation and energy wastage by enabling lights to turn on only at night and off during the day. This automation relies on the photoconductive property of the LDR. Its resistance decreases as the surrounding light increases. Now we see the advantages and disadvantages of the LDR sensor. The system block consists of LDR sensor and Arduino control, which continuously senses light intensity and sends an analog voltage signal to one of Arduino's analog input pins. We have low cost sensing by using LDR sensor and converts light to resistance and ease of integration and good linearity. And we also have some of the limitations, which is poor linearity and strong illumination, hysteresis effect, light flickering, etc. But we have one idea to overcome the light flickering, which is the setup of connect the capacitor in parallel with the fixed value resistor in your LDR voltage divider circuit. The larger capacitor value will provide more smoothing but will also increase the circuit's response time. And now we have the analog output for the LDR sensor, which is a sorry, LDR will produce a analog output value. We use analog read function which reads analog value, and here for LDR there is a 10-bit analog value. For that, we also know 2 power 10 is also resembles to 1024. So we get LDR output from 0 to 1023 based on sunlight. And LED is the resistance value which can take only up to 255 bits. So here we can see our code. Um, uh, See, by seeing this code, first let's look at the header file ldr.h. This file defines the hardware connections. Our LDR sensor is connected to analog pin A1, and here we will define garden light, which is a variable to the digital pin 3 for the Arduino board. We also have declared two functions, one to initialize LDR setup and another to control the brightness. Moving to the implementation in the LDR, moving to the implementation, uh, ldr.h includes custom header file for LDR related definitions, and we use void init LDR void function definition for initializing the LDR system. Here we use two variables which is ADC and LED. Those both are unsigned. Declares for ADC value and LED brightness. And we can see that formula for LED output is 255 minus ADC analog value divided by 4. We will divide here by 4 because the LED will take up to only 255 bit, but for LDR sensor we will get the voltage value up to 1024. So to reduce to 255 we will divide it this by 4. We can see here this example. Now for example, if the sunlight is maximum, the ADC value will be 1023, which is highest, and we will divide it this by 4, so we get 255. Then we will use our formula 255 minus this ADC value divided by 4, we get 0. So when the LED output value is 0, the light will not glow. Based on LED output value, the intensity of light increases with increase the output of output value.
Hello, this is Tarun. My topic is about temperature control system. In modern smart homes and industrial environments, maintaining a comfortable and stable room temperature is essential for both energy efficiency and user comfort. Traditional temperature control systems often rely on manual intervention or simply thermostats with limited functionality. To overcome these limitations, an automated and IoT-based temperature control system can be implemented to monitor and regulate temperature intelligently and remotely. This project presents a room temperature control system using an LM35 temperature sensor, an Arduino microcontroller, and the Blink IoT application. The process begins with the LM35 temperature sensor measuring the current room temperature. The LM35 converts this temperature into an analog voltage signal that is proportional to the actual temperature in degrees Celsius. The analog signal from the LM35 is sent to the Arduino Uno, which converts it to a digital value using its analog to digital converter. The Arduino then processes this data to determine the exact temperature reading. Once the temperature value is calculated, the Arduino performs two actions simultaneously. It sends the temperature reading to CLCD so that the temperature can be viewed directly on the device. It also transmits the temperature data to the Blink IoT app or an internet connection for remote monitoring. Also, it displays the gauge widget to monitor the temperature. On the Blink IoT app, the user can see the current temperature in real time. The app also provides on or off buttons to control the heater and cooler remotely. If the room becomes too warm, the user can turn on the cooler through the app. If the room becomes too cold, the heater can be turned on instead. The Arduino Uno receives these control commands from the Blink app and activates the corresponding devices in the temperature system. When the heater is on, the room temperature starts to rise. When the cooler is on, the room temperature decreases. Calculation. The LM35 outputs a voltage that's directly proportional to the temperature. This voltage is then read by the ADC of a microcontroller to calculate the temperature. The LM35 gives an output of 10 millivolts per degree Celsius. This output voltage is sent to ADC input pin A0. Now the ADC converts 0 to 5 volts analog signal into a digital value ranging from 0 to 1023 because it's a 10-bit ADC. The basic formula is ADC value equal to analog read of A0. The conversion range is straightforward. 0 volts corresponds to a digital value of 0 and 5 volts corresponds to a digital value of 1023. Next, let's look at how we convert that ADC value into voltage and temperature. The formula for voltage conversion is voltage equal to ADC value into step size. For example, if ADC value is 512, the voltage is 2.5 volts. If the ADC value is 200, the voltage is about 0.98 volts. This shows the direct link between the analog voltage and the ADC digital value. Now, to convert voltage to temperature, first read the ADC value, then convert it to voltage using the same formula. Voltage equal to ADC value into step size. Finally, convert the voltage to temperature. Temperature in Celsius equal to voltage by 10 millivolts. For example, if the ADC value is 50, then the voltage is 0.244 volts and the temperature is 0.244 divided by 0.01, which is equals to 24.4 degrees Celsius. Let's take a look at the header file temperature systems. This file defines all the constants, pin configurations, and function declarations related to the temperature control system. At the beginning, we have header guards. This prevents the file from being included multiple times during compilation. Next, we define the pins. Heater is connected to pin 4 and the cooler is connected to pin 5 and the temperature sensor is connected to the analog pin A0. Then we declare the main function used in the system, read temperature, to read the temperature from the LM35 sensor. Initial temperature system, to initialize all temperatures related components. Cooler control, to control the cooler on or off. Heater control, to control the heater on or off. Now moving on to the implementation file temperature system.cpp. Here we start by including the necessary header files, that temperature system.h and Arduino library and main.h. Inside the initialize temperature system function, we set up the heater and cooler pins as output using the pin mode of function. Next, in the read temperature function, we read the analog value from the LM35 sensor using analog read of A0. The formula used here is temperature equal to analog read of A0 into 5 divided by 1024. This converts the ADC value into voltage and then into temperature in degrees Celsius based on LM35 10 millivolt per centigrade output. The cooler control and heater control function both used as boolean variable named control. If control is true, the corresponding device is turned on using digital write pin now digital write function. Otherwise, it turned off with digital write pin, 0.
Good evening, everyone. Today, I would like to talk about the serial remote tank monitoring system, a smart and efficient setup that helps monitoring and control tank parameters such as water level, pressure from a distinct location using serial communication like UART RS232 or RS485. The A serial remote tank monitoring system is designed to monitor and control a tank's parameter from a remote place using serial data transmission. It collects data from sensors installed in the tank and sends the data to a remote display or control unit, allowing users to know the tank's status in real time. The main component used in this system is microcontroller, sensor, a serial interface, remote display, and a power supply. The working the working of this system is simple. First, the sensor measures the water or fuel level inside the tank. The microcontroller reads this sensor output and converts it to a readable digital value. This data then transmitted through serial communication either through wired or wireless means. At the receiver side, another microcontroller PC or HMI receives the data and display it on an LCD serial monitor or a SCADA system. Additionally, a relay can be added to the automatically control or motor or valve, turning it on or off based on the tank level. So, some of the applications of this system are industrial fluid storage tanks, water level monitoring in overhead or underground tanks, agriculture irrigation systems, fuel level monitoring in remote depots. Now, I will explain the actual process going on this total home automation project. So, the main goal of this project is to monitor and control the water level in a tank automatically using Arduino UNO, a CLCD display, and the blank IoT application. In this system, a water level sensor is placed inside the tank to measure the volume of water. The sensor sends this data to the Arduino UNO, which acts which acts which acts as the brain of the project. The Arduino then displays the current water level on a CLCD, so we can easily see how much water is present in the tank. Along with that, the system is connected to the Blink IoT app, which allows us to uh, monitor and control the tank remotely. Through the app, we can view the water level in real time and also control the inlet and outlet valves. For example, if the water level is low, we can open the inlet valve to fill the tank, and it is full, we can open the outlet valve to release water. The Arduino also sends a notification to both the CLCD and the Blink app when the tank is full or empty, ensuring proper management of the water usage. In short, this project helps in automating the water tank system, reducing manual effort, and efficiently controlling water flow through smart technology. Now, uh, I will explain the code which we use in this project, and you can see the flowchart of what happening in this project. Now, first I will explain about the serial tank.h code. Here, you can see in and out. In has a value of 0 into 00 and out has a value of 0 into 01. These are used when controlling inlet and outlet valves through serial commands. Here you can see high float and low float. This high float represents the high level float sensor in the tank. Low float represents the low level float sensor. They send signals when the water reaches top or bottom levels. You can see it take here, that is sent to request analog data in this case the tank level or volume reading from the tank unit. You can see enable and disable with 0 into 0 and 0. It resembles that enable equals to 1 turns on valve or action. Disable equals to 0 turns off valve. Now you can see these commands. These are function declarations. They tell the compiler which function exists and their types. The actual code for these functions will be in serialtank.cpp. So I will now explain serial tank.cpp. These are the header files as I said before, and uh, you can see these files here. These purpose is initializes serial communication between controller and tank system. you can see serial begin sets the baud rate to 19,200 bits per second for data transfer. The four serial write lines send synchronization bytes to align communication between devices like a handshake signal. So uh, now you can see unsigned input volume. This is a function, and in that you can see serial dot write take sends the command take to ask the tank module to send the current volume. Now you can see a while here. This its purpose is it waits until data is available to read from the serial port, then reads the high byte of the tank level and stores it in valor.h underscore h. Now you can see another one. The difference between these both is it waits until the high byte, and this one waits and waits again for another byte, the low byte, and then stores it in valor1. So now you can see valor. This combines both bytes into a single 16-bit number. Valor h. This one shifts the high byte to the upper 8 bits. Valor 1 merges the lower byte. This gives the final tank volume value. The function that returns this is valor. Now this function is used for in first in identifies the inlet valve. Second, enable turns it on. Together they open the inlet valve to fill the tank. So now you can see disable inlet function. In this serial write disable. It means inlet valve, and sends a command to turn off the inlet valve. The tank stops filling. And next you can see enable outlet and out and enable. It means the sends a command to open the outlet valve, allowing liquid to flow out, and this sends a command to close the outlet valve, closing the outflow. In summary, serial tank dot h uh, defines commands and declares functions, and serial tank dot cpp execute those commands using serial communication. Now you can see here functions inlet vpin and outlet vpin. Here the user controls the inlet valve by via blink app switch. When the user presses on and it enables enable inlet, this turns on the inlet valve. When off, disable inlet. This uh, turns off the inlet valve. It sends a off command via serial to close the valve. Similarly, like inlet vpin, outlet vpin also is a command which again uses this function from serial tank.cp to control the outlet valve through serial communication. Now you can see a handle tank function here. This function likely uses volume to read the tank level. Enable or disable is directly operated by this it automatically maintains automatically ons or off the system for maintaining safe water levels. uh, for saying an example, for example, if volume less than low limit, it enables the inlet valve, and if volume greater than high limit, it disables inlet valve. That way the tank fills automatically when low and stops when a closed loop automation system. Now you can observe here uh, initialize serial tank function. So this function purpose is to this initialize serial communication with the tank controller. For example, another Arduino or a module controlling balls and sensors. It runs the code from serial tank.cpp. So now your main controller is ready to communicate with the tank control unit via serial connection. You can see functions like blink run, timer run, and you can see volume equals to wall equal volume. This is the main function where we use serial tank.cpp. uh, this communicates with the tank system via serial connection to receive the water level in the tank. The value is then displayed on the LCD. So every loop your Arduino reads the tank volume through serial, updates the display, can take automatic actions like turning on or turn off. So that's the concept related to the code on a serial tank. How serial tank is connected to Arduino. We connect the serial remote tank to the Arduino by virtual connection.
This is my project simulation where you can see when I increase the resistance the light is on, and where I decrease the resistance the light is off. This resistance resembles the sunlight where we can control the garden lights, as you can see here now. Second requirement, temperature control system. As you can see, I displayed the interface. Now I turn on the heater. The temperature is increasing slowly. Now I am turning off, the temperature is off, heater is off. Now oning the cooler, the temperature is decreasing slowly, and the cooler fan is rotating also, as you can see side. Now I'm going to show that control system where heater is on, going beyond 35 degrees will turn off. Now you see the heater is on, so slowly the temperature is increasing. As it goes to around 35, the heater is automatically off. Yeah, temperature increasing. Right now the temperature is 35, the heater is off, where you can see in display. It turn off in interface also. This is my second requirement for this project. Coming to third project requirement, wait, I'm gonna adjust my widget. Yeah, because of my computer lag, it was difficult to operate it. As you can see, when the outflow is on, the volume should decrease, and when it comes lower than 2000, the inflow should on. Yeah, it automatically on. As you can see, it is 1950, the inflow is automatically on, that the volume of the tank is increasing slowly. Switching off the inlet valve is off, and oning the outflow, the draining of volume is happen. Offing the switch, the outflow is blocked. And this is our project simulation and presentation. Thank you.